Okay, so matrix inverses, not so much fun to compute in general, but sometimes there are nice formulae for inverses. They don't work in general, only work some of the time, special classes, but here is a wonderful example of a general inverse formula. Consider a square matrix A. Subtract it from the identity. I claim that there is a nice formula for the inverse of I minus A, and it's given by the following equation. We have I plus A squared plus A cubed plus A to the fourth, etc., etc., etc. Now, what is that? What does this even mean? What? It's like some sort of infinite series for matrices, and this doesn't seem all that easy, computing infinitely many powers of A. Whatever, don't worry about it. Let's just see something cool. Let's see that it works. I'm going to prove that this is a formal inverse by multiplying the two together. If I take I minus A times I plus A squared plus A cubed, etc., etc., what do? Well, I just multiply them. This is kind of like multiplying polynomials, right? I do that distribution. I take the identity times all that stuff. Multiplication by the identity does nothing, as you know. Then I subtract A times all that stuff. This just increments the exponents in the powers. And notice that if I line up the columns correctly, we get a tremendous amount of cancellation, and we're left with I, the identity. That means we have an inverse. Well, that means we have a right inverse. We need to multiply in the other direction to make sure that we have a full inverse, but, we can do that. That's great. Now, of course, I'm kind of stretching the truth here a little bit. This series, like many series, doesn't always converge. You remember your series, right? Oh, wait a minute. Now that you mention it, this series looks kind of familiar. Hey, this is the geometric series. This is our old friend. Remember back from single variable calculus when we saw this all the time. If I were to write down 1 over 1 minus A, you would expand this out into the following immediately. What is so lovely and so satisfying is how this works in matrix algebra as well.